Imagine you are awake in a dark, soundproof room. Complete silence. No light. Just you and your thoughts. How long could you remain sane? Hours? Days? For most people, the answer is shockingly brief. In 2008, scientists at McGill University placed volunteers in anechoic chambers, rooms designed to eliminate all sound with complete darkness. The intended duration was 2 weeks. Within hours, participants reported hallucinations. By 48 hours, most were begging to leave. Why? Because your brain abhors emptiness. When deprived of external input, it manufactures its own reality. The silence becomes voices. The darkness transforms into shapes and colors. Your mind would rather create a false reality than endure no reality at all. This is not a failure of perception but a glimpse into your brain's hidden machinery. Machinery that operates constantly beneath your awareness, filtering, enhancing, predicting, and sometimes fabricating your experience of reality. And it is just one of dozens of secret strengths your brain conceals from your conscious mind. The hallucinations experienced in sensory deprivation reveal something profound. What we call reality is actually a controlled hallucination, a best-guess model of the world created by your brain. The difference between this everyday hallucination and those experienced in sensory deprivation is simply the quality of the input data. Your brain is not a passive receiver of information but an active constructor of your reality. And this construction happens automatically, invisibly, and with such seamless integration that we never notice the machinery at work. We simply experience the final product, a coherent world that feels unquestionably real. Dr. Sarah Yardley, a neuroscientist at the University of California, Berkeley, explains it this way. What we experience as reality is actually the brain's model of reality, a simulation based on incomplete data that has been heavily processed, filtered, and augmented before reaching consciousness. This is a story about the extraordinary, hidden abilities of your brain, abilities that shape every moment of your existence, yet remain largely unknown to you. We will journey through the latest discoveries in neuroscience that reveal how your brain performs feats of perception, memory, prediction, and creation that would be considered superhuman if they were conscious abilities rather than automatic processes. These are not merely academic curiosities. Understanding these hidden strengths changes how we think about human potential, the nature of consciousness, and even what it means to be human. And while some of these abilities might seem like limitations or even liabilities, they each evolved for crucial survival purposes. They are the unacknowledged foundation upon which your conscious experience is built. Our journey begins with perhaps the most fundamental yet overlooked fact about your brain. It operates in near-total darkness, sealed inside your skull, never directly experiencing the world it so convincingly portrays. Your brain weighs approximately 3 pounds, roughly 2% of your body weight, yet consumes 20% of your energy. Inside your skull, it sits in complete darkness, bathed in cerebrospinal fluid, receiving information only through the electrical signals transmitted by your sensory nerves. It never sees light, hears sound, or feels touch directly. Instead, it receives encoded data, patterns of electrical impulses that it must decode and assemble into what we experience as reality. This presents an extraordinary challenge. How does a brain, isolated in darkness, create the rich, seamless experience of a three-dimensional world in vivid color, with depth, movement, and meaning? In 1991, Dr. Richard Langdon conducted an experiment that revealed just how actively our brains construct our visual experience. He showed participants images of faces for just milliseconds, too briefly for conscious recognition. Yet when later shown the same faces among others, participants preferred the previously flashed faces, despite having no memory of seeing them. Their brains had processed and stored information their conscious minds had never perceived. The conscious mind, says Dr. Rachel Lowenstein, cognitive scientist at MIT, is like the CEO of a vast corporation who receives only the final reports, never witnessing the complex operations that produce them. Consider vision. When you look at a friend's face, you experience a stable, clear image. You do not see the blood vessels crisscrossing your retina, though they are always present in your field of vision. You do not notice your blind spot, the area where your optic nerve connects to your retina, though every human eye has one. And you do not perceive the constant microsaccades, tiny eye movements that occur several times per second. Your brain actively eliminates these imperfections, filling in the blind spot with predicted information based on surrounding visual data. It stabilizes the image despite your constant eye movements. It enhances edges and contrasts to make objects stand out from backgrounds. And it does all this before you consciously see anything. This processing happens with astonishing speed. Visual information travels from your retina through several processing stations before reaching your visual cortex. At each station, different aspects of the image are extracted and enhanced. Some neurons respond only to horizontal lines, others to vertical lines. Some detect movement, others color. By the time the information reaches your conscious awareness, it has been thoroughly transformed. Dr. Stephen Yoshida of Johns Hopkins University puts it bluntly, "We don't see the world as it is. We see it as our brain thinks it should be, based on past experience and evolutionary priorities." This raises a profound question. If our conscious experience is so heavily processed and filtered, what else might our brains be hiding from us? What other extraordinary abilities operate beneath the surface of awareness? And how might understanding these hidden strengths change our perception of human potential? As we will discover, the construction of visual reality is just the beginning. Your brain possesses abilities that would seem like superpowers if they were accessible to conscious control. From precognition-like prediction to memory manipulations that would make science fiction writers envious, the machinery of your mind harbors capabilities that redefine what it means to be human. And as we explore these hidden strengths, a fascinating pattern emerges. Many of these abilities remain unconscious not because of some biological limitation, but because consciousness would actually interfere with their operation. Your brain, it seems, deliberately conceals its most impressive abilities from your conscious awareness for your own good. The next question, then, is one that will guide our journey. What exactly is your brain hiding from you and why? Your brain is a prediction machine. While you consciously process the present moment, your brain is already anticipating the future. Not minutes or hours ahead, but milliseconds. This predictive capability operates constantly, forecasting everything from the trajectory of moving objects to the next words in a sentence. In 2013, neuroscientists at the University of Glasgow designed an experiment that revealed just how aggressively your brain predicts the future. Participants watched videos of everyday actions like someone pouring tea. Using fMRI scanning, the researchers discovered that brain regions activated before predictable actions occurred, not after. Your brain was not reacting to events but anticipating them, preparing perceptual and motor systems for what it expected to happen next. This predictive capability explains a puzzling fact. Professional baseball players cannot actually see a fastball throughout its entire journey to the plate. A 95 miles per hour fastball takes approximately 400 milliseconds to reach home plate. Human visual processing and motor reaction requires at least 200 milliseconds. Add the time needed to swing a bat, and hitting the ball becomes mathematically impossible. If players were simply reacting to what they see. Batters don't hit the ball they see, explains Dr. Samuel Young, a sports neurologist. They hit the ball their brain predicts will be there. The greatest hitters aren't those with the fastest reflexes. They're those with the most accurate predictive models. This predictive capability extends to social interactions. When having a conversation, your brain constantly forecasts what the other person will say next, preparing responses before they finish speaking. This is why conversations flow naturally despite the complexity of language processing. Your brain is running simulations of possible conversational paths, allowing you to respond appropriately without consciously computing every possible interpretation of their words. These predictions happen automatically and unconsciously. You cannot feel your brain making these predictions. You only experience their results. When predictions are accurate, you never notice them. When they fail, you experience surprise. But perhaps the most striking example of your brain's predictive nature is revealed in research by Dr. Benjamin Libet in the 1980s. Using electroencephalography, EEG, Libet discovered something remarkable. The brain activity associated with voluntary movements begins approximately 200 milliseconds before you become consciously aware of your intention to move. In other words, your brain decides to act before you, your conscious self, knows about it. This finding has profound implications for our understanding of free will and consciousness. It suggests that what we experience as conscious decision-making may actually be the brain informing consciousness of decisions it has already initiated. Your sense of being the author of your actions may be, in some sense, a narrative constructed after the fact. Dr. Rachel Lowenstein explains, consciousness appears to be more like a witness to brain activity than its initiator. Your brain computes and decides, then informs consciousness, which creates the subjective feeling that I made the decision. This doesn't mean free will is an illusion. It just operates differently than our intuitive understanding suggests. Rather than consciousness directing all action, it may instead have veto power, the ability to override automatic brain processes when needed. Like a CEO who doesn't micromanage every detail but retains authority to intervene when automatic processes go awry. Your brain's predictive nature extends beyond motor movements to perception itself. In fact, what we perceive is a complex blend of sensory input and predictive modeling, weighted toward whichever is more reliable in a given context. This is why optical illusions work. They exploit the predictive mechanisms that normally help us perceive accurately. Consider the blind spot in each eye. You don't perceive holes in your visual field because your brain fills in the missing information based on surrounding context. This filling in happens so seamlessly that most people are unaware of their blind spots until specifically tested for them. The implications of these findings are extraordinary. Your brain constructs your experience of reality by blending actual sensory data with predictions based on past experience and statistical patterns. When predictions match incoming data, perception feels effortless. When they conflict, your attention is drawn to the mismatch, forcing conscious processing to resolve the discrepancy. This leads to another hidden strength: your brain's ability to maintain a coherent model of reality by filtering out irrelevant information. A capacity that shapes every moment of your conscious experience, yet operates entirely beneath awareness. At this moment, your brain is performing an astonishing feat of filtration. Your skin contains approximately 200,000 sensory receptors reporting pressure, temperature, and texture. Your ears are detecting sound waves across a range of frequencies. Your peripheral vision registers movement and color across a wide field. Your body's position in space, muscle tension, and internal organ functions generate constant sensory feedback. Yet you notice almost none of this. Why? Because your brain filters out approximately 99% of all sensory information before it reaches consciousness. In 1953, cognitive psychologist Colin Cherry discovered what he called the cocktail party effect. Your ability to focus on a single conversation in a noisy room while filtering out all other voices. This selective attention demonstrates your brain's remarkable capacity to prioritize relevant information while suppressing everything else. But the full extent of this filtration remained unknown until 1998, when neuroscientists Nili Levy and Yehoshua Tzal developed load theory, demonstrating that your brain's filtering mechanisms operate automatically based on the perceptual and cognitive demands of tasks. Their research revealed that we consciously perceive only information that survives multiple layers of neurological filtering. If consciousness had access to all sensory data simultaneously, explains Dr. Stephen Yoshida, we would be overwhelmed to the point of paralysis. Filtration is not a limitation but a crucial adaptation. A dramatic demonstration of this filtering in action comes from the famous Invisible Gorilla, experiment conducted by Christopher Chabris and Daniel Simons in 1999. Participants watched a video of people passing basketballs and were instructed to count the passes made by players wearing white shirts. During the video, a person in a gorilla costume walks through the scene, stops in the center, beats their chest and walks off. Remarkably, approximately 50% of viewers failed to notice the gorilla. This phenomenon, called inattentional blindness, reveals how our brains filter out information deemed irrelevant to current goals, even when that information is bizarre and would normally be highly salient. Your brain decides what deserves your conscious attention, and it makes these decisions without consulting you. The implications are profound. What we experience as reality is not simply the world as it exists, but the world as filtered through our brain's attention mechanisms. And these mechanisms are tuned by evolution to prioritize survival-relevant information, not necessarily to provide a complete or objective picture of reality. Even more remarkably, your brain doesn't just filter incoming sensory data, it actively suppresses certain types of self-generated information. Consider your ability to ignore the sensation of your clothes touching your skin throughout the day. Your sensory neurons are constantly reporting this tactile information, but your brain filters it out as irrelevant unless something changes. This filtering extends to higher cognitive functions as well. Your brain constantly generates thoughts, impulses, and emotions, many of which never reach consciousness. Freud called this the unconscious mind, but modern neuroscience has given us a more precise understanding of how these filtering mechanisms work. Research using fMRI has shown that when you make a decision, your brain activates multiple competing response patterns before selecting one for conscious awareness. The alternatives are inhibited through a process called lateral inhibition, where the strongest neural pattern suppresses its competitors. You only become aware of the winning thought, never experiencing the competition that preceded it. Dr. Rachel Lowenstein compares this to a political system. It's like your brain holds a constant electoral process, with competing neural coalitions vying for the presidency of consciousness. You only ever meet the winner, never the runners-up. This explains why solutions to problems sometimes appear to come from nowhere after a period of not thinking about them. Your brain continued processing beneath consciousness, and only when a solution reached sufficient strength did it break through into awareness. Perhaps most fascinating is how this filtering shapes our sense of self. Your brain maintains a coherent self-model by filtering out information that would threaten this coherence. Studies on choice blindness, conducted by researchers at McGill University, demonstrate this powerfully. When research subjects were tricked into believing they had made choices they hadn't actually made, they readily confabulated explanations for these choices, unaware that they were justifying decisions they never made. Your sense of having a stable, consistent personality is partially maintained by this filtering. Your brain suppresses awareness of behaviors, thoughts, and feelings that contradict your self-image, creating what psychologists call the illusion of continuity. This isn't always beneficial. When filtering becomes too rigid, psychological problems can emerge. But in general, this hidden strength allows you to maintain a functional self-concept despite the chaotic and often contradictory nature of human cognition. As we continue our exploration, we'll discover how these filtering mechanisms work in concert with another hidden strength: your brain's capacity for memory manipulation, a system far more creative and fallible than most people realize. "I remember it like it was yesterday." This common phrase reveals a profound misconception about memory: the belief that memories are like recordings, stored perfectly and replayed when needed. The truth is far more complex and fascinating. Your memories are not recordings but reconstructions, assembled anew each time you remember them. In 1974, cognitive psychologists Elizabeth Loftus and John Palmer conducted a groundbreaking study demonstrating the malleability of memory. Participants watched films of automobile accidents and were then asked questions about what they saw. Simply changing one word in the question, asking how fast cars were going when they smashed versus hit each other, caused participants to estimate significantly higher speeds and report seeing broken glass that wasn't actually present in the film. This revealed something profound. Memory is susceptible to suggestion and can be altered after formation. Unlike a computer file that remains unchanged unless deliberately edited, human memories transform subtly each time they're accessed. When you remember something, explains Dr. Stephen Yoshida, you're not retrieving a static record but reconstructing an experience based on fragments of information combined with your expectations, beliefs, and subsequent experiences. This reconstructive nature of memory might seem like a flaw, but it represents an extraordinary adaptive strength. Rather than storing perfect records of every experience, which would require enormous neural resources, your brain preserves the elements most likely to be useful for future prediction and decision-making. The neural mechanisms underlying this process were discovered by neurobiologist Karim Nader in 2000. His research demonstrated that when memories are recalled, they enter a labile state where they can be modified before being reconsolidated. This process, called reconsolidation, allows memories to be updated with new information, keeping your knowledge base current without requiring separate storage for each version of a memory. This explains why eyewitness testimony is notoriously unreliable despite witnesses' confidence. Each time they recall the event, during police interviews, conversations with lawyers, and courtroom testimony, the memory reconsolidates, potentially incorporating new details suggested by questions or other influences. More dramatically, research by cognitive neuroscientist Elizabeth Phelps has shown that emotional arousal during memory recall enhances reconsolidation, making emotionally charged memories particularly susceptible to modification. This explains why traumatic memories often change over time and why different people remember shared emotional experiences differently. But perhaps the most startling aspect of memory's reconstructive nature is the phenomenon of false memories, entirely fabricated recollections that feel subjectively identical to true memories. In a series of experiments beginning in the 1990s, Elizabeth Loftus demonstrated that approximately 30% of participants could be led to develop detailed false memories of childhood events that never occurred, such as being lost in a shopping mall or taking a hot air balloon ride. These implanted memories were indistinguishable to participants from their authentic memories. The brain doesn't mark memories with a true or false label, says Dr. Rachel Lowenstein. The subjective experience of remembering doesn't tell us whether something actually happened, only that our brain has constructed a coherent narrative incorporating certain elements. This reconstructive process extends beyond episodic memories, memories of events, to semantic memories, general knowledge, and even to your life narrative. Your sense of who you are, your personal history and identity, is continuously revised as your brain reconstructs your past to maintain coherence with your present self-concept. Studies tracking people's life narratives over time show that autobiographical memories shift to support current goals and self-image. Achievements become more central to the life stories of successful professionals, while relationship milestones gain prominence in the narratives of those who prioritize family life. These shifts occur largely outside awareness. You don't experience yourself actively editing your past, yet your memory does exactly that. This hidden strength serves crucial functions. It allows your knowledge to remain relevant by integrating new information with old. It maintains psychological coherence by aligning your past with your present identity. And it enables imagination and planning by recombining memory elements into novel scenarios. Indeed, recent neuroimaging research by cognitive neuroscientist Demis Hassabis revealed that the same neural networks active during memory retrieval also activate when imagining future events or fictional scenarios. Your brain uses the building blocks of memory to construct possible futures, a capacity essential for planning and decision-making. Dr. Samuel Young explains, memory's primary purpose isn't to preserve the past, but to inform future behavior. Its reconstructive nature allows flexible adaptation rather than rigid adherence to past experiences. This perspective transforms how we understand memory's imperfections. Forgetting, memory distortion, and even false memories are not simply flaws in an otherwise perfect system. They are features of a memory system optimized for adaptation rather than perfect recall. A system designed to help you navigate an uncertain future rather than document an unchangeable past. As we'll discover next, this reconstructive memory system works hand in hand with another hidden strength: your brain's capacity for unconscious learning and implicit knowledge acquisition, abilities that allow you to know far more than you can explain. In 1997, a chess grandmaster faced an unusual challenge. He was blindfolded and played against 7 opponents simultaneously. Not only did he win 4 games and draw 2, but he accurately recalled the final position of every piece on all 7 boards. When asked to explain how he performed this seemingly impossible feat, he could not articulate his method. This demonstration reveals another hidden strength of your brain: its ability to learn complex patterns and develop expertise without conscious awareness of the underlying processes. Neuroscientists call this implicit learning, the acquisition of knowledge that occurs without intention or awareness. There are 2 fundamentally different ways we learn, explains Dr. Stephen Yoshida. Explicit learning involves conscious effort and attention. Implicit learning happens automatically, without awareness, and often yields knowledge we cannot verbalize. This distinction was first demonstrated scientifically in studies of amnesia patients who, despite being unable to form new conscious memories, could still learn new motor skills. Patient HM, who underwent bilateral removal of his medial temporal lobes to treat epilepsy in 1953, lost the ability to form new explicit memories. Yet when taught a mirror drawing task, his performance improved each day, even though he had no recollection of ever practicing. Similar implicit learning happens in healthy brains constantly. In a classic experiment by Arthur Reber in 1967, participants were shown strings of letters generated by a complex set of grammatical rules. After exposure to multiple examples, they could accurately judge whether new strings followed these rules, despite being unable to articulate what the rules were. They had implicitly learned the grammar without conscious awareness of doing so. This capacity for implicit learning extends to social interactions. Psychologist Nalini Ambady conducted thin-slicing research showing that people make accurate judgments about others' personalities, teaching ability, and even sexual orientation based on just seconds of observation. These judgments occur too quickly for conscious analysis, suggesting they arise from implicit pattern recognition. Your brain is constantly absorbing statistical patterns from your environment, says Dr. Rachel Lowenstein. Much of what we call intuition or gut feeling is actually the conscious manifestation of this implicit learning. The neural basis for this ability involves multiple brain systems working in parallel. While the hippocampus and prefrontal cortex support explicit, conscious learning, the basal ganglia and cerebellum enable implicit learning of procedures and patterns. This explains why you can become proficient at activities like driving or typing without consciously thinking about each movement. Perhaps most remarkably, research indicates that implicit learning often outperforms conscious learning for complex tasks. In studies by psychologist A.P. Dijksterhuis, participants made better complex decisions, such as apartment selection based on multiple criteria, when their conscious attention was diverted than when they deliberately analyzed options. The unconscious mind excels at integrating multiple factors simultaneously, while conscious thought tends to fixate on limited aspects of a problem. This has profound implications for expertise development. Neuroscientist Michael Shadlin's research reveals that experts in domains from medicine to chess develop neural networks specialized for rapid pattern recognition. These networks operate largely beneath consciousness, allowing experts to make accurate judgments based on subtle cues they cannot explicitly identify. A dramatic example comes from studies of firefighters by psychologist Gary Klein. Experienced fire captains sometimes ordered their crews to evacuate buildings moments before unexpected collapses, saving numerous lives. When interviewed, they often attributed these decisions to gut feelings or sixth sense. Deeper investigation revealed they had unconsciously detected subtle cues, unusual heat patterns, or uncharacteristic sounds, that their implicit learning systems recognized as dangerous without conscious awareness. This hidden strength explains why experts often struggle to teach their expertise. Master musicians, artists, or athletes frequently resort to metaphors and analogies rather than explicit instructions because much of their knowledge exists in neural patterns inaccessible to conscious introspection. When we ask experts to explain their intuition, Dr. Samuel Young notes, we're asking them to translate knowledge from one neural format to another, from implicit patterns to explicit language. It's like asking someone to describe the taste of strawberries using only geometric terms. Your brain's capacity for implicit learning serves crucial functions. It allows efficient processing of environmental regularities without taxing limited conscious resources. It enables rapid responses in situations where deliberate analysis would be too slow. And it facilitates the development of expertise that transcends what could be achieved through conscious learning alone. But this strength comes with trade-offs. Because implicit knowledge operates beneath awareness, it resists conscious examination and correction. This explains why implicit biases persist despite conscious intentions, and why habits are so difficult to change through willpower alone. Understanding this hidden strength changes how we approach learning and decision-making. Rather than relying solely on conscious analysis, we can create conditions that optimize implicit learning through immersion, varied practice, and occasional periods of distraction that allow unconscious processing to occur. As we'll explore next, this implicit learning system connects to another remarkable hidden strength: your brain's capacity for unconscious problem-solving, the ability to reach solutions through processes that occur entirely outside awareness. In 1865, chemist Friedrich August Kekule had been struggling for years to determine the chemical structure of benzene. The solution came not through methodical analysis but in a moment of relaxation. As he dozed by the fire, he dreamed of a snake biting its own tail, a vision that inspired the breakthrough idea of benzene's ring structure. This famous example illustrates another hidden strength of your brain: its ability to solve problems unconsciously, often producing solutions that emerge into awareness as sudden insights or eureka moments. Cognitive neuroscientist Mark Beeman has spent decades studying this phenomenon, which he calls the aha moment. Using EEG and fMRI technology, Beeman and colleagues identified distinct neural signatures that precede these moments of insight. Approximately 300 milliseconds before a person consciously experiences an insight, there's a burst of gamma band activity in the right temporal lobe, a neural marker of pieces falling into place beneath conscious awareness. These findings suggest that insights aren't random, explains Dr. Stephen Yoshida. They're the culmination of extensive unconscious processing that suddenly crosses a threshold into consciousness. The mechanics of this process were further revealed through studies using remote associates tests, RATs, where participants must find a word that connects three seemingly unrelated words, e.g., pine, crab, and sauce, are connected by apple. Researchers found that the brain continues processing these problems even when attention shifts elsewhere. In fact, participants often solved problems more successfully after a period of distraction than after continuous conscious effort. This unconscious problem-solving ability has been demonstrated across domains from mathematics to creative writing. Mathematician Henri Poincaré documented how his most significant insights occurred during periods of relaxation after intensive work. Modern research confirms this pattern. Intensive focus on a problem followed by periods of distraction often leads to breakthrough insights when the mind returns to the problem. The neural basis for this ability involves what neuroscientists call the default mode network, DMN. Interconnected brain regions that become more active when you're not focused on external tasks. First identified by neurologist Marcus Raichle in 2001, the DMN enables your brain to explore associations, connections, and possibilities without the constraints of goal-directed thought. The default mode network allows your brain to make remote associations between ideas that conscious, linear thinking might never connect, says Dr. Rachel Lowenstein. It's why solutions often come during a shower, a walk, or while falling asleep, times when the DMN is highly active. This explains why forcing an insight rarely works. Conscious effort engages task-positive networks that can actually suppress the default mode network. The ideal approach involves alternating between focused attention and strategic distraction, what psychologists call the oscillation method of problem solving. This hidden strength operates not just in creative or intellectual domains, but in everyday decision-making. In a series of studies on deliberation without attention, psychologist A.P. Dijksterhuis demonstrated that for complex decisions with multiple factors, like choosing an apartment or car, people make better choices when their conscious mind is distracted after initial information gathering, allowing unconscious processing to integrate the many variables. Perhaps most remarkably, your unconscious problem-solving machinery operates continuously, processing information and generating potential insights even during sleep. Matthew Walker's research at UC Berkeley shows that sleep, particularly REM sleep, helps the brain identify non-obvious connections between previously learned information. Participants in memory and problem-solving tasks performed significantly better after a night's sleep compared to equivalent periods of wakefulness. This ability to solve problems unconsciously reflects your brain's parallel processing architecture. While conscious thought proceeds serially, one idea after another, unconscious processing can explore multiple possibilities simultaneously, testing countless combinations before presenting the most promising candidates to consciousness. Consciousness is like a spotlight, Dr. Samuel Young explains. It illuminates details with precision but can only focus on a narrow area at once. Unconscious processing is more like ambient lighting, less intense but covering a much broader territory. This explains why forcing yourself to think harder about a problem often proves counterproductive. When stuck, the most effective approach is often to load your brain with relevant information, focus intensely on the problem, then deliberately turn your attention elsewhere, trusting your unconscious machinery to continue working. The implications extend beyond individual problem-solving to collaborative innovation. Research on group creativity shows that the most productive brainstorming sessions include periods of individual incubation, time away from the group when each person's unconscious processing can operate without the constraints of social dynamics. Understanding this hidden strength transforms our approach to innovation and problem-solving. Instead of equating productivity with constant conscious effort, we can design workflows that leverage unconscious processing, incorporating incubation periods, sleep, and strategic distraction as essential components of the creative process. As we'll explore next, this unconscious problem-solving capability connects to perhaps the most remarkable hidden strength of all, your brain's capacity for self-modification, its ability to physically rewire itself in response to experience, a phenomenon known as neuroplasticity. On January 13, 2011, U.S. Representative Gabrielle Giffords was shot in the head at point-blank range. The bullet passed through the left side of her brain, the hemisphere responsible for language processing in most people. Medical experts predicted she would likely never speak again if she survived. Yet within months, Giffords was speaking in full sentences. Within years, though still recovering, she was giving public speeches. This remarkable recovery demonstrates another hidden strength of your brain, its capacity for self-modification through neuroplasticity, the ability to reorganize neural pathways and even reassign functions to different brain regions in response to experience, learning, and damage. For most of the 20th century, neuroscientists believed the adult brain was largely fixed, with significant plasticity existing only during childhood developmental periods. This critical period theory suggested that certain abilities, like language acquisition or vision development, could only be established during specific developmental windows, after which the brain lost its capacity for substantial reorganization. This view was dramatically overturned by a series of experiments beginning in the 1960s. Neuroscientist Paul Bach-Wierita developed devices that allowed blind people to see by transforming visual information into tactile sensations on their skin. Remarkably, Participants' brains learn to interpret these touch patterns as visual information, activating visual cortex areas despite receiving input through entirely different sensory channels. The brain, Bhakwi-Rita concluded, is massively plastic, capable of reorganizing in response to the information it receives, rather than being hardwired to specific sensory inputs. The full extent of neuroplasticity became clear through research with stroke patients by Edward Taub in the 1990s. Taub developed constraint-induced movement therapy, which forced patients to use their affected limbs by constraining their unaffected ones. This approach triggered significant brain reorganization, with healthy regions taking over functions previously performed by damaged areas, even years after the initial stroke, long past when recovery was thought possible. The mechanisms of neuroplasticity operate at multiple levels. At the cellular level, neurons that fire together strengthen their connections through a process called Hebbian plasticity, summarized by the phrase neurons that fire together, wire together. At the network level, entire brain regions can be repurposed based on use patterns. And at the structural level, the brain can grow new neural connections and even generate new neurons in certain regions throughout life, a process called neurogenesis. Your brain physically rewires itself based on your experiences, explains Dr. Stephen Yoshida. Every skill you practice, every fact you learn, every habit you form creates physical changes in your neural architecture. These changes occur through multiple mechanisms. Existing neural connections can be strengthened or weakened. New connections can form through the growth of dendritic spines, tiny protrusions on neurons that receive input from other cells. And in certain brain regions, particularly the hippocampus, entirely new neurons can be generated throughout life. The scale of this remodeling is astonishing. Learning a new skill like juggling produces measurable growth in gray matter volume within weeks. Becoming a taxi driver in London, which requires memorizing thousands of streets and routes, significantly enlarges the posterior hippocampus, a brain region involved in spatial memory. Even more remarkably, your brain can compensate for significant damage through functional reorganization. In cases of hemispherectomy, surgical removal of an entire cerebral hemisphere, sometimes performed to treat severe epilepsy, children can develop nearly normal cognitive functions as the remaining hemisphere takes over tasks typically performed by the missing half. Dr. Rachel Lowenstein explains, the brain isn't organized around physical structures so much as functions. If one region can't perform its typical role, other regions can often adapt to take over, preserving the function even when the original hardware is compromised. This plasticity extends beyond compensating for damage to enhancing normal function through training. Research on musicians shows enlarged motor and auditory regions compared to non-musicians, with the degree of enlargement correlating with years of practice. Similar structural differences appear in the brains of mathematicians, taxi drivers, and bilingual individuals, all reflecting experience-dependent brain remodeling. Perhaps most encouragingly, research by neuroscientist Michael Merznick demonstrates that this plasticity persists into old age. While the rate of change may slow, the fundamental mechanisms remain operational throughout life. Merznick's studies show that older adults engaging in targeted brain training can reverse age-related cognitive decline and even regain neural processing speeds typical of much younger individuals. The implications of neuroplasticity transform our understanding of human potential. Intelligence, talent, and ability are not fixed quantities determined solely by genetics but dynamic properties that can be developed through properly structured experience. The brain you have today is not the same brain you had a year ago, and it's not the same brain you'll have a year from now. It is continuously remodeling itself based on how you use it. This hidden strength operates largely beneath awareness. You don't feel your brain forming new synapses or reorganizing neural maps. You simply notice improved performance after practice or gradual recovery of function after injury. The machinery of plasticity works silently, changing the physical substrate of your mind without conscious supervision. Understanding neuroplasticity changes how we approach education, rehabilitation, and personal development. It reveals that the brain's capacities are far more malleable than previously believed, and that structured training can produce profound changes in neural architecture and function at any age. As we'll explore in our final section, this capacity for self-modification connects to what may be your brain's most remarkable hidden strength of all. Its role in constructing not just your experience of the world, but your very sense of self, your consciousness. In 1848, a 25-year-old railroad foreman named Phineas Gage suffered a horrific accident. An iron rod shot through his skull, destroying much of his left frontal lobe. Remarkably, Gage survived. But according to contemporaneous accounts, his personality changed so dramatically that friends said he was no longer Gage. Once responsible and mild-mannered, he became impulsive and profane. This historic case provided the first evidence of a profound truth. What we experience as our self, our personality, preferences, and core identity, is a construction of our brain. When the physical brain changes, the self changes too. Modern neuroscience has confirmed this insight through increasingly sophisticated methods. Using transcranial magnetic stimulation to temporarily disable specific brain regions, researchers can induce dramatic but temporary changes in personality, moral reasoning, and even religious belief. Pharmacological interventions affecting neurotransmitter systems can transform someone's emotional responses, decision-making tendencies, and subjective sense of identity. The most profound hidden strength of your brain, says Dr. Rachel Lowenstein, is its ability to create the experience of having a self at all, to generate the sense of being a continuous, unified person moving through time despite the constant physical changes occurring in your brain and body. This self-constructing ability operates through several mechanisms. Your brain maintains autobiographical narratives, stories about who you are and how you came to be, continually updating them to preserve coherence. It generates a sense of agency, the feeling of being the author of your actions, by predicting the sensory consequences of movements and matching them against actual outcomes. And it creates the experience of ownership over your body through multisensory integration of touch, vision, proprioception, and other inputs. The constructed nature of selfhood becomes visible through various neurological and psychological phenomena. Consider the condition known as depersonalization, where people experience a detachment from their sense of self, feeling as if they're observing themselves from outside. This occurs when brain networks involved in self-representation become desynchronized from sensory processing networks, revealing that the normal sense of inhabiting your body and life is an active construction rather than an inevitable given. Similarly, certain meditation practices can temporarily suspend the sense of having a separate self. Neuroimaging studies of experienced meditators show decreased activity in the default mode network, brain regions involved in self-referential thinking, during states of selflessness. This demonstrates that the experience of being a distinct self is generated by specific brain activity patterns that can be modulated. What's remarkable, explains Dr. Stephen Yoshida, is not just that your brain constructs your sense of self, but that it conceals this construction process from you. You don't experience yourself actively generating your selfhood. You simply feel that you are. This concealment serves important functions. By presenting selfhood as discovered rather than created, your brain allows you to navigate life without constantly questioning your fundamental nature. Provides a stable platform from which to interact with the world and others. And it creates the sense of continuity necessary for long-term planning and social relationships. Yet this construction is more flexible than it appears. Research on identity change following major life transitions, such as career shifts, religious conversions, or recovery from addiction, reveals how thoroughly self-narratives can be revised. People often describe these transitions as becoming who I really am, experiencing their new identity as more authentic despite its recent emergence. Dr. Samuel Young notes, "What feels like discovering your true self is actually your brain constructing a new self-model that better integrates your current values, behaviors, and social context." Neither the old nor new self is more real. Both are constructions serving different needs at different times. This hidden strength, the brain's self-constructing capability, explains numerous psychological phenomena. It accounts for how people maintain consistent self-images despite contradictory behaviors by selectively attending to evidence supporting their self-concept and discounting contradictory information. It explains why emotional events feel more self-defining than neutral ones. They trigger stronger activity in self-representation networks. And it illuminates how cultural differences in self-conception emerge, as brains construct selfhood using culturally provided conceptual resources. Perhaps most profound are the implications for identity development and personal growth. If selfhood is constructed rather than discovered, then transformative change becomes more conceivable. Your sense of who you are isn't a fixed essence to be uncovered, but an ongoing creation that can be thoughtfully reshaped. This doesn't mean selfhood is arbitrary or infinitely malleable. Your brain constructs your self-model based on biological predispositions, accumulated experiences, and social feedback, all genuine constraints. But within these constraints lies considerable flexibility, as evidenced by the dramatic identity changes people sometimes undergo through therapy, spiritual practice, or life transitions. Understanding this hidden strength transforms our approach to personal development. Rather than trying to find yourself, you might focus on creating yourself, deliberately engaging in experiences and practices that shape your brain's self-constructing processes in desired directions. As Dr. Rachel Lowenstein puts it, your brain doesn't just show you the world and yourself as they are. It creates models of both, models that are useful rather than perfect, adaptive rather than comprehensive. Recognizing this creative power is perhaps the most profound insight neuroscience offers, that who you are is partly your own creation. We began this journey by considering a profound paradox. Your brain, sealed in darkness inside your skull, creates your entire subjective experience of reality, yet conceals its own operations from your awareness. We've explored the hidden strengths that operate beneath consciousness, from predictive processing and selective filtering to memory reconstruction, implicit learning, unconscious problem-solving, neuroplasticity, and self-construction. These discoveries reveal something remarkable. Consciousness is not the commander of mental operations, but more like their witness. Your conscious experience is the product of vast unconscious machinery that evolved not to provide perfect accuracy but adaptive utility. Dr. Stephen Yoshida puts it this way: evolution favored brains that created useful models over those that created complete ones. Your brain shows you what you need to see to survive and thrive, not everything that exists. This perspective transforms our understanding of human nature. The limitations we often bemoan, our susceptibility to illusions, biases in memory and perception, constraints on conscious processing, are not design flaws but necessary features of a system optimized for effectiveness rather than accuracy. Similarly, what we celebrate as uniquely human capabilities, creativity, insight, expertise, adaptability, self-awareness, emerge largely from processes operating beneath conscious control. They are not achievements of consciousness but gifts from our unconscious machinery. This new understanding changes how we might approach human potential. If many of our most impressive abilities operate outside conscious control, then maximizing performance may involve creating conditions that optimize unconscious processes rather than attempting to control everything consciously. For learning, this means embracing the oscillation between focused attention and strategic distraction that allows implicit learning and unconscious problem-solving to occur. For creativity, it suggests balancing information gathering with incubation periods that engage default mode network activity. For personal growth, it implies working with rather than against your brain's natural tendencies, using its plastic nature to gradually reshape neural patterns rather than fighting established networks through willpower alone. Perhaps most profoundly, recognizing the constructed nature of conscious experience, including your sense of self, offers both humility and empowerment. Humility comes from acknowledging that your perception of reality and selfhood are models, not direct access to ultimate truth. Empowerment comes from realizing these models can be refined and reshaped through deliberate practice and experience. As Dr. Rachel Lowenstein observes, understanding these hidden strengths doesn't diminish human dignity or agency. If anything, it enhances them by revealing capacities more remarkable than we previously imagined. Your brain's hidden strengths represent one of the most extraordinary evolutionary achievements in natural history. The development of an organ that can model both the external world and itself with sufficient accuracy to enable language, technology, culture, and self-reflection. That we are beginning to understand how these capacities work is itself a testament to the brain's remarkable capabilities. The journey through your brain's hidden strengths ultimately reveals this. Your conscious mind is not the entirety of your being, but the visible surface of a vast, intricate system whose operations largely remain concealed. Yet it is precisely these concealed operations, these secret strengths your brain hides from you, that make possible the richness of human experience and the depth of human potential. Your conscious self is not diminished by this realization but expanded, connected to capabilities more profound than typically acknowledged. For beneath the stream of consciousness flows the deeper current of the unconscious mind, carrying the accumulated wisdom of evolution and experience, shaping every moment of your awareness while remaining itself just beyond the reach of that awareness. In the end, perhaps the most remarkable secret your brain hides is this: you are both more and less than you imagine, less consciously in control, yet endowed with capabilities far exceeding what consciousness alone could achieve.